Welcome to another segment of High School Geometry with Netz and Weichel. This is Mrs. Netz.
And this is Mrs. Weichel.
And today we are looking at 8.3 Circle Theorems. What will we be learning? Well, by the end of the lesson, you will be able to determine a missing segment length. Why do you need to know this? Well, the relationships will tie prior relationships together, showing how intertwined math is. How will you know it? You'll know you mastered it when you can identify the different theorems given various types of segments and lines.
All right, so this lesson is going to look and seem very similar to the previous lesson in 8.2. 8.2, if you look at the pictures from the notes and if you look at today's pictures, a lot of them look the same. Just one thing to keep in mind when you have all of these different things to remember for a test, yesterday or 8.2 dealt with angle relationships, so we were dealing in the measurements of degrees. Whereas today, while the same lines are forming the same angles, now we're looking at the lengths of the segments rather than the degrees formed. So similar but not the same. So the first one that we're going to be looking at is when you have a radius intersecting a tangent line. So remember, a radius is just half a diameter, which is a chord going through the center. And then a tangent is a line that is completely outside a circle, intersecting the circle at one point. Now, because in 8.2 we learned about how a chord and a tangent angle measurement is half of the intercepted arc, and we know a diameter splits a circle in half, this angle must be exactly half of 180, or half a circle. So we know that this angle is always going to be 90 degrees. So a tangent is perpendicular to a radius. Now, as far as what types of problems you'll be doing, you're going to be using right triangle problems. So most of the problems that you're going to be doing will use Pythagorean theorem. So you'll always have an external point, the point of tangency, which is where the tangent intersects the circle, and then the center of the circle, forming that right triangle. Most problems, again, will use Pythagorean theorem, but you could use trigonometry or special right triangles if we gave you information that led you towards using that information. The next one, we have tangent, tangent. So if you look at this one, notice that all you're dealing with are two tangents on the outside of our circles. If I were to create a triangle right here, I would know that this angle here is equal to exactly half of this intercepted arc because it's a chord tangent from 8.2. I know that this angle would be exactly the same due to the fact that it's intercepting the same arc, making these two angles congruent, making this an isosceles triangle. So because that's an isosceles triangle, I know that those pieces are equal. These are the two congruent sides in that isosceles triangle. So two tangents that intersect outside the circle are going to be congruent to each other. So you just set them equal and solve. When you have a chord and a radius, if you have a radius that is perpendicular to a chord, so here's a radius intersecting a chord, and they are perpendicular to each other, we also know that the chord is bisected. The converse to this also works. So if you have a radius bisecting a chord, then the radius is perpendicular to the chord. So you will know both. And similar to the first one we looked at with a radius and a tangent, we will mostly use Pythagorean theorem with this if I were to draw a radius connecting O to Q or O to P. Basically, here's your A, B, and C for Pythagorean theorem. But if we gave you some angle measurements, you could do trigonometry as well to find the missing side lengths. For chord, you are going to create proportional segments. The reason you are able to do this, here's an inscribed angle. This inscribed angle is exactly half of this arc. This is also an inscribed angle, but it's intersecting the same exact arc. So you know these two angles will always be congruent to each other. Down here is exactly the same thing, and you have a pair of vertical angles. So therefore these are similar triangles, and we remember from chapter 6 that similar triangles create proportional pieces. So for A to C in this triangle, it would be the same as D to B in this triangle because of that similarity piece. Please notice, though, just really quickly, there aren't any triangles here. But if you were to create triangles, you can see that proportional or similar relationship between the two. The last two are a little bit more tricky, but again, it comes back to actually similar triangles. So if I were to explain this, don't get alarmed by this. Let me explain where this is coming from. They're similar colors, but hopefully you can see this lighter orange color triangle right here. The side opposite the obtuse angle is this I plus E side. It's the inside part plus the outside part of this secant. And then you have these two acute angles. This acute angle is important because it's part of both triangles. This is an inscribed angle, which is half of this arc. Well, if you look at the darker orange triangle, which is this one, you have this same angle, and then this inscribed angle, which is intercepting the same exact arc. So you know these are congruent angles. So therefore, these are similar triangles, making those proportional pieces. So if you look at again, the lighter color, the I and E on the top is opposite the obtuse angle. If you look in the bottom triangle that's facing this way, the darker one, here's your obtuse angle. Well, what side is opposite that? The O and the C together. So that's how this side came to fruition. Then if you look back at this original one, we don't have anything written on this side of the triangle, but we do have something here. We have O. And then if you go to the other triangle, the same side would be E. So we have I and E and O on top. And then for the other triangle, you have O and C, and then E on the bottom. These are reflected. It's a reflection. So you can see that we're here and here. And then if you reflect this triangle, you're here and here.
So you're basically comparing same parts to same parts. And if you use your congruency marks to help you figure out your matching parts, you'll have an easier time with this. So basically, when we say E plus I, you're comparing the very long side of that triangle, okay, to O and C, which is the very long side of the other triangle. Now, here's the part that may be a little bit more challenging to see. We are now going to say that side E, it actually goes with that O and C because it's part of the same triangle. So that's why it looks like we've kind of flopped the letters, but we haven't. That E goes with the OC. And the O is a short piece on the other triangle that actually does go with that long side of EI. So while it looks like you've kind of flopped the letters to go with the wrong triangle, we really haven't.
And that flip-flop that happens is always going to happen. So if you have something like this, the way I kind of show it, you're looking at the top, comparing it to the bottom, and then you look at the bottom and you look at the top. Total top, total bottom, and then outside bottom and outside top because of those proportional, similar, corresponding pieces. And then lastly, we have our secant tangent, which is going to actually have the same exact relationship as the secant secant. We're going to create similar triangles, and through similar triangles, we are able to make proportional pieces. So we have our secant here with I and E for exterior, interior, and then we have our tangent. If I were to make triangles, so we have the big triangle. So the big triangle uses the entire secant, the tangent, and then this chord inside here that I have added. We have I and E together, and we have T. If you notice, those are the denominators of my proportion. Then I have my triangle right here. If you look at these pieces, you have just E and just T. If you look, those are your numerators. So as far as knowing where everything goes, this inscribed angle is half of this arc. Well, this chord tangent angle is half of the same arc. So these are congruent angles. Then this is part of both. So again, here's my obtuse angle. What is opposite the obtuse angle? I and E. In the smaller triangle, what is opposite the obtuse angle? T. So there's my first ratio. In my small triangle, what is opposite this chord tangent angle? E. When I go to the same angle in my larger triangle, this inscribed angle is opposite T. So E over T. Another way you could think of it, I'm going to bring back our right triangle similarity. You could think of the tangent as the geometric mean between the entire secant and the outside part or the external part of the secant. So if you remember, geometric means meant you squared it and then you multiplied the other pieces. Well, the other pieces are going to be the secant and the outside part of the secant. So in this problem, what is the secant? Well, it's e and I together. What's the outside part? E. You can see that when you solve this, that's what you're multiplying. And then the tangent squared, so that's your geometric mean. So you can think of it that way.
Perfect.
All right, so let's go ahead and do these. So in order to determine which of the 6 formulas you're given, you really just have to look at what types of lines or line segments you're given. Like, for example, here, you're given a radius for RS and a tangent of ST. So radius tangent, we know they are perpendicular. And when we know they're perpendicular, you can make a right triangle and use right triangle steps to solve a problem like this. I'm telling you RT is 5 and ST is 4, so this is Pythagorean theorem. To find the radius, that's going to be your A side or B side. 4 and 5 are your B and C respectively. So you work this out. I'm not going to spend a whole lot of time. This is just a basic 3, 4, 5 triangle if you work it out. So the radius of this circle would be 3. For this one, AZ is a tangent, CZ is a tangent, so this is the tangent box you need to be looking at. And we determined, if you remember, that this is an isosceles triangle if I make it, so we know AZ is equal to CZ. So you're simply going to equal these and solve it. If you would like to work this out and check your answer, please go for it. Otherwise, I'm just going to go on because this is just a simple equation to solve. You end up getting 3x minus 4 is equal to 9x minus 16. Using your properties of equality, you end up getting that x would equal 2. For this problem, if you look at your notes, there isn't a single problem that looks really like this. However, you have just tangents. So you're going to look at the tangent one. Where you just had tangents, you know that technically speaking, that is an isosceles triangle. Right here, this is an isosceles triangle. And then right here, this would be an isosceles triangle. So this problem is actually no different than the one we just solved where we set them equal to each other. You just have 3 of them rather than 1 of them.
Just be very careful and please make a note. Put a big star. The most common mistake. Please make note of it. This, you want to write yourself a note. Don't do this. We see it all the time. Someone will do it. We're trying to warn you. Don't do it. We will have students all the time assume that n is a midpoint and that bn equals ni, and that is not the case at all, because we know tangents are equal to tangents, and bn is not the matching tangent to ni.
Right. So yeah, these are not midpoints. I don't care how I drew it for you or how Mrs. Ness drew it for you. What you are able to conclude is that if LO is 9.5, LD is 9.5, because these are equal. If OB is 16, then BN is 16 because these are equal. And then if NI is 15, then so is DI because these are equal.
Now, all you have to do, because we're trying to figure out the perimeter, is you just have to add everything up. So basically what we are saying at this point is you would then take 2 times 9.5, 2 times 15, 2 times 16, add all of that up, and you get your perimeter is 81 units.
Perfect. So this one also looks nothing like any of the problems on the front side of your guided notes or the formulas that we looked at.
I love this problem. I love these.
But if you just look at the segments given, you should be able to figure out which one we're looking at. So 20 is a radius. The vertical segment is also a radius.
So that
Horizontal.
radius is also 20 because all radii in a circle are all congruent.
And then lastly, this horizontal piece is a chord. If you look in your notes, you were given something about a radius and a chord. You were given that if a radius is perpendicular to a chord, that the chord is bisected. So you know that this is congruent to this. If you remember what I told you you're going to be using to solve this, you're going to be probably doing Pythagorean theorem or something with right triangles, which means we need to draw a right triangle. So if I know the radius is 20 and it can be drawn anywhere, like Mrs. Neth said, we are able to draw a radius right here, which will make our right triangle. Because I know 24 is the entire length of the chord, and I know the chord is bisected, then I know this must be 12 and this must be 12. This is another one where you need to make yourself a note. The chord is bisected. The radius is not. So with a problem like this, I have had students just tell me that x, or the distance to the chord, would be 10 because half of the radius is 10. That is not how this works. If one thing is bisected, that doesn't make everything bisected. The rule for this is strictly saying that if you have a radius and chord that are perpendicular, then the chord is bisected.
And if you truly think that it is a bisector, then I want to strongly encourage you to double check. And all you have to do to double check is do 10 squared plus 12 squared should equal 20 squared if it is indeed bisected. You're going to find it's not.
It's not. So this is just another simple Pythagorean triple. It's actually another 3, 4, 5 triangle that is dilated by a scale factor of 4. 3 times 4 is 12, 4 times 4 is 16, and 5 times 4 is 20. 3, 4, 5 triangle.
This problem is a lot like the last problem. So we have a radius of 17, and then we also have another radius of 17. While I know you see the 9 there, I get that, but that 9 is only the distance from, it's a part of the radius, and it goes from the chord to the circumference of the circle. So we need to figure out how long the chord is. Well, we know the radius is 17, we know a piece of the radius is 9, so that leftover piece of the radius has to be 8, because 8 plus 9 is 17. So I also know that because I have a chord and a radius, that it has been bisected. So I know that both sides have got to be equal to the same thing. But I'm not going to worry about that just yet. Right now, I'm just going to do Pythagorean theorem and do 8 squared plus x squared is equal to 17 squared. Then I go ahead and solve, and I find that x is equal to 15. Well, x is equal to 15, and the problem asks, find the length of the chord. On your test, there will be an answer choice, 15, and it's wrong.
And so many students get this wrong. They did all the work right, they knew what to do, but then they get the problem wrong.
Because you put that x is 15, you get so excited your answer is there. And I agree with you, x is 15, but the length of the chord is 2x. So therefore, the length of the chord is going to be 30.
So huge note on that one. You're going to see this question again, I promise you. Make sure you read the question and double your answer at the end. Okay, so this one, where the 3 and the x are is a chord, where the 4 and the 6 are, that's a chord. So we have two chords. If you look at the other side of your notes, we know that the chord creates proportional relationships. Remember, we have our similar triangles here. So the way we set up our proportion is similar to how we did the triangle proportionality theorem, in that you're just basically looking at the picture to see what's over what. So if you look here, 3 is on top. It is on top of 4. 6 is on top, and it is on top of x. So we're going to simply make our proportion look like that.
And if you remember correctly from our notes, we were actually able to draw the actual proportion within the problem using the numbers that are there, because we just, on the actual problem, we just put a fraction bar between 3 and 4, an equal sign right in the middle, and then a fraction bar between the 6 and the x. So this problem, for the most part, sets itself up.
Exactly. And then after you have it set up, you're simply going to cross multiply. giving you simply 3x is equal to 24. Then you're going to divide the 3 out, and you get 8. And then again, we have the two more difficult ones, so please pay attention to these to make sure you feel confident on how to work through these for your practice. Even though you don't see it, we have a secant here that we can connect to this point that would create a triangle with a side length of 5 plus 6 and 4. And then I can also make a triangle with this entire secant on the bottom connecting to here with a side length of x and 4 and then the 6. We know that we can make those triangles similar through angle-angle similarity, which means I can make a proportion. If you look at the secant on top, whenever you see something added together, you have to look for the two pieces. And when we're dealing with circles, usually those pieces are inside and outside pieces. So if you're looking at the top here, your two pieces are the 5 and the 6. On the bottom, we're also adding. So the other piece that has the outside and inside are the x and the 4. Because we have to keep corresponding pieces together, you're now going back to the triangle that had the 5 and the 6. The other side, if you remember, I said was 4. So this is going to be the O. In the similar triangle where we had the x and the 4, the other side of the x and the 4 was 6. So you're going to plug it in just like this. You have the 5 and the 6 and the 4 on top, and then on the bottom you have the x and the 4 and the 6 because they are part of the same triangle. Once you plug that in, the problem becomes a lot easier. You're just going to solve this proportion. So you know 6 plus 5 is 11. You are going to cross multiply at this point, giving you 6 times 11 is equal to 4 times 4 plus x. Please don't forget right here, everybody tells me to distribute. Everybody knows they get 16 here. Please do not forget the second part of the distributive property, which would give you that 4x. Then through the subtraction property and the division property, you end up getting 25 over 2. And then the last problem is our secant tangent. Remember with this one, from the point of tangency to this point, I can make a triangle. If I have a triangle right here, it has a side length with the 4 and 5, and then the x. The other triangle I can make from this intersection to the point of tangency has two side lengths of x and 5. So when I'm looking at the formula that was in your notes, the adding part has the interior and exterior parts. That's the 4 and the 5. That is opposite the obtuse angle in the larger triangle. If I look at the smaller triangle, here's my obtuse angle. What side is opposite that? X. So where 4 and 5 are, I'm going to put x in the same fraction or same ratio. Then I'm going back to the big triangle. The only other side I have, you have the 4 and the 5 we used. The other side is this x. Well, that is opposite that inscribed angle. Well, what angle is the same as the inscribed angle in the small one? It's this chord tangent angle. So I'm going to compare x to 5. And here we have it. You have the 5 and 4 together and the x. Those are from that larger triangle. The smaller triangle, you have x and 5 in from the smaller triangle on the bottom. And then again, from here, you're going to just cross multiply. We know that 5 plus 4 is 9, and x times x is x squared. 5 times 4 gives me 45, and then when you have an x squared, you must square root both sides. Square root of 45 is the correct answer, but it is not a simplified correct answer. So just know that when you prime factor 45, you are able to take out 3 square root 5.
So basically, you could think of the square root of 45 as the square root of 9 times 5. And you know that the square root of 9 is 3.
And the square root of 5 is not rational, so you can't solve it.
Square root of 5. That's all you got.
All right, so that is the conclusion of our lesson 8.3. So again, it's just more picture matching. Hopefully you guys feel confident that you can tell the difference between your chords, secants, tangents, and radii/diameters. If not, please reach out to us as always.
Hey, Mrs. Weichel.
Hey, what, Mrs. Nets?
So, you know why our video lessons are so much shorter than our in-person lessons?
Why?
Well, when the students are here, we tend to go off on a tangent.
That is so true. I think sometimes they make us go off on tangents, but
You mean it's on purpose?
what's funny about that is that's just less time for them to get stuff done.
They do it on
I
purpose?
think they do. Isn't that messed up?
Sneaky, because we never did that when we were in school.
Never.
Never.
All right, thanks so much for joining us. Our next lesson is going to be about arc lengths when we're talking about 8.4.